The hearth of a blast furnace is the ultimate black box. It's where your operational stability either solidify or catastrophic failure begins. So we have all seen what happens when liquid level get out of control. It's not just a production delay, it's a threat to the entire asset. On the title slide, you see a high visualization of liquid flow vectors highlighting the chaotic turbulence we are fighting every day. In this session, we are going to dive deep into three critical deliverables. First, defining the 70 minutes cliff edge, that is as per the furnace volume, 79 minutes of the hard voidage. Second is the forensic telemetry fusion to predict the cast delays. And third, the specific refractory purity threshold required to maintain Taphole integrity. So by the end of this hour, you will have a new protocol for reclaiming stability in your furnace most hostile environment. To understand the stakes, we have to look at the mathematical tipping point where the furnace physics start working against us. Now look at the furnace cross section on the left. Notice the red arrow pushing down and the turbulent pink swill rising in Hearth. So this visualizes the moment uncontrolled liquid violently destabilizes our thermodynamics. That line is our critical failure threshold. If the liquid reaches the weir level at 4.6 meter, submerged coke begins to float. This is not just a level issue, it physically crushes the cohesive zone from below, choking buoyant descent and causing that massive 25% blast pressure spike you see in the table. So here everything is clear. You have exactly some limited time, and that time as per this furnace volume is 79 minutes to fill your hearth voidage before the furnace choke. Once you cross that 79-minute mark, you have lost the continuous cast state and enter a high risk recovery mode that destroy your daily throughput. Now, managing this cliff phase requires more than just a level probe. We need a forensic approach to our sensor data. So, coming to coming here, we introduce the data fusion core. So, follow the green circuit line connecting our macro sensors. On the left, we are pulling in furnace EMF for submerged voids at 1 minute interval. On right, look at the granulation water and the torpedo ladle icon. We are not just looking at temperature, we are measuring continuous slack thermometry and the mass flow rate in the kilogram per second. By marrying this telemetry with the microforensic refractory data, we expose the hidden variables that dictate catastrophic cast delays. The operational impact is significant. If your torpedo ladle mass flow starts dropping while slack temperature remains high, you have got a localized hearth blockage. So if you wait for the level probe to tell that you are already behind the curve, use this fused data to predict the delay before the cast flow even report it. This is fantastic. So one of the most critical variable we track through this fusion is the impact of gap time on your protective layers. So this slide, which is yes, so this slide features a striking exponential graph. The x-axis is a time in minute and y-axis is the hearth level in the meters. So look at the blue line. For the first few minutes, the rise is linear. The 30-minute mark, but at the 30-minute, the curve turns red and skyrockets. Simultaneously, look at the table at the upper right. At 4 minutes, you have a 96% slack coverage protecting your hearth wall. By 60 minutes, that coverage dropped to less than 40%. This is the gap time. A delay doesn't just raise the level, it destroys the protective slag layer, exposing your carbon brick to direct liquid iron contact. And this exponential rise alter furnace physics so rapidly that a 30-minute delay can take 30 hours of a stable operation to thermally recover from. So while we manage the time between cast, we also have to manage the geometry of the taphole itself, starting with the drill diameter. And the drill diameter is supposed to be very important aspects. So on the left in the cool blue is the target 50 drill diameter. The flow lines are smooth and parallel. This is the laminar stability. On the right, the 60 reactive diameter is shown as a chaotic jagged red blast. Operators often over drill to solve a slow cast, but this is an illusion of progress. So look at the data. That extra 10 turns your flow turbulent, resulting in a hot metal yield loss of over 2.5% per cast. Even worse, it takes 5 subsequent casts to recuperate that size back to the baseline. So you are trading today's minor crisis for a week of instability. Every time you go to a 60 bit, you are actively destroying the laminar separation in your runners and killing your yield. Keep it all 50 or you will never find your thermal equilibrium. So now coming to the beyond the drill size, the chemical composition of the clay matrix determine how fast that hole wears down. And on this we see two pillars representing different clay matrix. The tall green pillar is our sintered alumina tar mix with a wear rate of only 0.15 millimeter per minute. Contrast that with a short glowing red pillar representing standard plus fast resin. Fast curing resin are popular because they save time, but look at the cost. They double your taphole wear rate. This allows for massive retained slag in the hearth because the hole enlarges too quickly during the cast. And here is a campaign life issues also occurring. So by choosing the high purity sintered alumina matrix, you maintain a safe liquid level of 1.0 meter. If you use the fast resin shortcut, you are consistently operating in 1.5 meter danger zone, inviting premature erosion of the hearth pad. So excessive wear doesn't just happen at the face, it initiates deep within the structure through secondary cracking. So this slide is a cross section of the taphole bore. Notice the glowing concentric rings representing the PS stages, process, structure, performance. So look at the depth marker at 3.0 meter. We have a high pressure gas leaks at 2 meter. Structural fissures lead to secondary liquid drains, and finally at the face you get a performance blow or a premature dry signal. So this is the so what of taphole forensic. These internal cracks cause false dry performances where the operator thinks the furnace is empty but the hearth is actually still half filled. So you and your or you can say you end up plugging the hole early, leaving liquid behind and setting the stages for a hard chill. We must eliminate this secondary crack if we want to trust our dry signals again. So when these cracks and wear rates are not uniform across all tapholes, we develop a dangerous asymmetry in the hearth. And this upcoming slide compares two hearth state. State A on the left shows a symmetrical tapping with the two 3.5 meter taphole. The slack to metal ratio is a stable 1.2 to 1.0. Now look at the state B. Taphole 2 has a shortened 2.8 meter. Notice the skewed tapping icon. The liquid flow is now biased toward the shorter, easier path. This swing your slag ratio widely, dropping taphole 2 down to a 0.6 to 1 ratio. This means you are pulling mostly metal and leaving the slag behind. The operational impact is a viscous hearth. The slag accumulate, create a thermal insulator and eventually leads to a chilled hearth. So maintaining equal taphole length is not just about a refractory, it is about maintaining the thermochemical balance of the entire furnace. So one of the primary reason we lose that taphole length and face integrity is poor plugging technique. So our slide shows these five wise staircase to find the root cause of spillage. So look at the illustration of the hydraulic mud gun on the right. We often blame clay viscosity for poor sealing, but look at why number 3. The evidence shows the high velocity gun collision. When the gun deaccelerate too late, it create a taphole partial sealing. So these collision create those secondary cracks we just discussed and destroy clay compression. And we have a question then, so what? So factor is immediate damage phase means you lose the seal, leading to spillage and uncontrolled gas tracking. To fix this, we don't need bitter clay. We need controlled ram or pushing, we can say. You have to treat that taphole face like a precision engineering gasket, not a target for a battering ram. So to keep these variables in check, we operate according to a specific liquid operating map. So what is that liquid operating map is going to be explained in the next slide. So we have our emerald zone protocol. So look at 3 color bands: green, yellow and coral. So this is 0.0 to 1.5 meter range. Uh, that is a stable open hearth void is where you maintain full blast volume. Once you hit the yellow zone at 1.5 to 3 meter, the burden is compressed and you must reduce the top pressure to assist descent. So if you hit the coral zone at the 4.6 meter, you are in a 2-year flood scenario. This requires an emergency stop. The operational imperative is simple: stay in the emerald zone. Crossing that threshold float the submerged coke and irreversibly compress the cohesive zone, as we discussed in our earlier slide. If you spend too much time in the yellow or coral, you are essentially aging your furnace by a month in a single shift. So staying in that emerald zone requires understanding the web of influence between our mechanical variables. So the web of influence, which is spoken by our this slide, which shows the mathematical correlation between our key metrics. Notice the R values in the table. Gap time has a 0.94 plus correlation with the maximum liquid level. That's a near perfect strong link. Clay wear rate is tied at 0.88 to retained slag, and drill bending is at 0.91 for hole enlargement. So this is a way: if you drill bend, the hole enlarges, your wear rate spikes. Your wear rate spike, you leave the slag behind. Leaving slag behind increases your gap time risk. The so what here is that micro deviation at the taphole mathematically dictate your macro thermodynamics. So you cannot manage the furnace temperature if you are not managing your drill alignment and clay purity first. So this stability wave must extend all the way out to the cast house runner, where we seek laminar separation. And our next slide, which is talking about the all similar aspect on the laminar trough separation. The top image shows the turbulent flow. It's a mess of interface chaos and slag iron mixing. These turbulence actively destroy your hot metal yield and crucially prevent effective desulfurization. So now look at the laminar flow. You see a stable interface with a clean separation. The data table tells the whole story. Laminar flow has a plus minus 2 centimeter interface depth and only 0.1% yield loss. So turbulent flow has a plus minus 15 centimeter depth and kills your yield by over 2.5%. So for a 3 million ton per year furnace, that 2.4% difference in yield is pure profit lost to the slag pit. So stable furnace dynamics are the final step in the securing economic value of your hot metal. Unfortunately, when things goes wrong, operators often reach for the oxygen lance, a move that carries a heavy penalty. Slide 13 visualizes the damage of a manual oxygen lances. So look at the 3D terrain map. That jagged glowing red canyon is the oxygen lance burn path. It is erratic and off axis. Contrast that with the nitrogen oblique mist trail, which keep the bore 100% centered. The so what is in the uh, block life rather forecast, using oxygen to open a frozen Taphole guarantee a 30% reduction in your campaign life. You drop from a 5-year block life to less than 3.5 year. It's an act of operational uh, validism for short-term gain. If you have to use oxygen, you have already failed at hearth management. We must prioritize mechanical opening method to preserve the refractory surface and the integrity of the hearth. To prevent the need for the lancing, we must eliminate the cracks that lead to frozen holes through the automated curing. So this slide shows the transition from manual step to auto post pressing. On the left, the orange wireframe is a shattering. This represents the propagation of micro crack under manual pressure. On the right, the green wireframe is solid and stable. Automated post pressing achieves over 95% crack filling compared to less than 40% with a manual step. This reduces false blow incidents from 12 per month down to just one. The operational impact is a massive reduction in unplanned wind stack. By upgrading to the automated curing, you eliminate the micro crack before they propagate, ensuring that every plug is a permanent high pressure seal that can be reliably drilled the next time around. So we bring all these concepts together into a single actionable strategy for the next campaign. And our this slide tells the new protocol. This is your mandate for the hearth stability. First, enforce laminar runner separation to reclaim that 2.5% yield. Second, upgrade to automated post pressing and high purity sintered alumina clay to eliminate microcracks and secure your Taphole length. And third, lock in rigid gap limit, no more than 10 minutes of variance to prevent the cohesive zone crash. So if you reclaim these variables, you reclaim the furnace. You move from a state of the hard dilemma to a state of operational mystery.